With Starbucks Holiday Blend for Nespresso Vertuo, now exclusively at Target, there are even more ways to share the joy. Savor every smooth and festive sip all holiday season with friends and family at home to fill every indulgent day with cheer.
This is SpaceTime Series 25, Episode 76, for broadcast on the 11th of July, 2022. Coming up on SpaceTime. New research suggests the dark side of the universe might not be all that real after all. NASA's Capstone moon probe finally phones home after mysteriously going silent for 2 days. And NASA's second launch in the Arnhem Space Centre blasts off to study Alpha Centauri. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
New research suggests the accelerating expansion of the universe due to a mysterious quantity known as dark energy may not be real after all, at least not according to ongoing research, claiming it might simply be an artefact caused by the physical expansion of the cosmos. The findings, reported in the monthly notices of the Royal Astronomical Society, claims a fit of Type 1a supernovae to a model universe with no dark energy appears to be slightly better than the fit using the standard dark energy model. The study's lead author, Professor David Wiltshire from the University of Canterbury in New Zealand, says existing dark energy models are based on a homogeneous universe in which matter is evenly distributed. However, as we all know, in the real universe, things are far more complicated. It comprises galaxies, galaxy clusters, and superclusters arranged in a sort of giant cosmic web with sheets and filaments of stars and galaxies surrounding near vast empty voids. Current models of the universe require dark energy to explain the observed acceleration and the rate at which the universe is expanding. Scientists base this conclusion on measurements of the distances to Type 1a supernovae in distant galaxies, which appear to be further away than they should be if the universe's rate of expansion wasn't accelerating. Type 1a supernovae are powerful explosions, bright enough to briefly outshine entire galaxies. They're caused by the thermonuclear destruction of a type of star known as a white dwarf, the stellar corpse of a sun-like star. All Type 1a supernovae are thought to explode at around the same mass, a figure known in astrophysics as the Chandrasekhar limit, which equates to about 1.44 times the mass of our Sun. Now, because they're all exploding at about the same mass, they all explode with about the same level of luminosity. And this allows astronomers to use them as standard candles to measure cosmic distances across the universe. It's exactly the same as the way you determine how far away a row of streetlights are along a road by how bright each light appears from where you're standing. In physics, it's known as the inverse square law. On a galactic scale, gravity appears to be stronger than scientists can account for using the normal matter of the universe, the material of the standard model of particle physics, which makes up all the stars, planets, buildings, and people. To explain their observations, scientists have invented dark matter, a mysterious substance which seems to only interact gravitationally with normal matter. Scientists know dark matter is real because they can see its effect on galaxies, holding them together as they rotate. Without dark matter, galaxies would literally fly apart. They've calculated there must be at least 5 times as much dark matter as normal matter in the universe to explain science's observations of how galaxies move. But on the even larger cosmic scales of an expanding universe, gravity appears to be weaker than expected in a universe containing only normal matter and dark matter. And so scientists have invented a new force called dark energy, a sort of anti-gravitational force, causing an acceleration in the expansion of the universe out from the Big Bang 13.82 billion years ago. Dark energy isn't noticeable at small scales, but it becomes the dominating force of the universe on the largest cosmic scales, almost 4 times greater than the gravity of normal and dark matter combined. It was the late great Professor Albert Einstein who first came up with the idea to explain a problem he was having when he first applied his famous 1915 equations of general relativity theory to the whole universe. You see, like other scientists of the time, Albert Einstein believed the universe was in a steady, unchanging state. Yet, when applied to cosmology, his equations showed that the universe wanted to expand or contract as matter interacts with the fabric of space-time. Matter tells space-time how to curve, and space-time is telling matter how to move. To resolve the problem, Einstein introduced a dark energy force in 1917, which he called the cosmological constant. It was simply a mathematical invention or fudge factor, and it was designed to solve discrepancies between general relativity theory and the best observational evidence of the day, bringing the universe back into that steady state. Of course, years later, astronomer Edwin Hubble discovered that galaxies appear to be moving away from each other, and the rate at which they were moving was proportional to their distance. The further away a galaxy was, the faster it appeared to be accelerating. With this revelation, Einstein realized his mistake, describing the cosmological constant as the biggest blunder of his life. However, the idea of a cosmological constant has never really gone away. In fact, it keeps reappearing to explain strange observations. In the mid-1990s, two teams of scientists, one led by Brian Schmidt from the Australian National University and Adam Rees, and the other by Saul Perlmutter, independently measured distances to Type 1a supernovae in the distant universe, finding that they appeared to be further away than they should be if the universe's rate of expansion was constant. The observations led to the hypothesis that there must be some kind of dark energy anti-gravitational force at work which has caused the expansion of the universe to accelerate over the last 6 billion years. But Wiltshire says these observations are based on an old model of expansion that hasn't really changed since the 1920s. You see, back in 1922, Professor Alexander Friedmann used Einstein's field equations to develop a physical cosmology governing the expansion of space in homogeneous and isotropic models of the universe. Wiltshire says Friedmann's equations assumes an expansion identical to that of a featureless soup with no complicating structures. And this has become the basis for what today is the standard lambda cold dark matter cosmology used to describe the universe. Wiltshire points out the unfortunate fact that in reality, today's universe is not homogeneous. The earlier snapshot of our universe, captured as a faint afterglow of the Big Bang and called the cosmic microwave background radiation, displays only slight temperature variations caused by differences in densities present 270,000 years after the Big Bang. The cosmic microwave background radiation has cooled to just 3 degrees above absolute zero, and the universe has become a vast cosmic web dominated in volume by empty voids, surrounded by sheets of galaxies, and threaded by wispy filaments of stars. Rather than comparing the supernova observations to the standard lambda cold dark energy cosmological model, Wiltshire and colleagues have used a different model known as timescape cosmology. Now, timescape cosmology has no dark energy. Instead, it includes variations in the effects of gravity caused by the lumpiness of the structure of the universe. Wiltshire says that clocks carried by observers in galaxies differ from the clock that best describes the average expansion once inhomogeneity becomes significant. He says whether or not one infers accelerating expansion then depends crucially on the clock being used. Wiltshire points out that timescape cosmology gives a slightly better fit to the larger supernova data catalogue than lambda cold dark matter cosmology. But he admits the statistical evidence isn't yet strong enough to definitely rule in favour of one model over the other. Wiltshire says future missions such as the European Space Agency Euclid spacecraft will have the power to distinguish between differing cosmology models. And another problem involves science's understanding of Type 1a supernovae. You see, in reality, they're not perfect standard candles. Since timescape cosmology uses a different equation for average expansion, it gives scientists a new way to test for changes in properties of supernovae with distance. Regardless of which model ultimately fits better, a better understanding of all this will increase the confidence with which scientists can use these practices in order to develop precise distance indicators. Wiltshire says answering questions like these will help scientists determine whether dark energy is real or not, an important step in determining the ultimate fate of the universe.
Einstein invented dark energy 100 years ago when he first applied relativity to cosmology, and for a different reason to the reason we use it now. Back then he mistakenly wanted to exactly balance the self-attraction of matter by some sort of anti-gravity on larger scales, and that's because he couldn't imagine that the universe had a beginning and he didn't want it to change with time. But really nothing was much known about the universe in 1917. The very idea that the nebulae were galaxies at vast distances was a matter of something called the Great Debate. So he faced a dilemma because, as he would know, the essence of his theory is that matter tells space how to curve and space tells matter how to move, which means the natural state of anything with an attractive force from the point of view of Newton is that space will naturally want to expand or contract, bending together with matter. It never stands still. So in order to get round that, he put in this extra anti-gravity force to balance the fact that space moving with matter, which is universally attractive, will generally want to pull together.
He was never really happy about that, was he? It was always something that bothered him a little bit because there's a fudge factor, and he knew that. Yes.
The reason that he wasn't happy was that the universe putting that thing in as a fudge factor is unstable. So mathematically, it's not a good solution. So there are various reasons why you could be happy or unhappy with it, because it's a very deep question in physics also. There are various levels of how you can answer that question.
Well, all that became moot when Edwin Hubble realized that galaxies appear to be virtually all moving away from us.
Correct. So that's why he went back on the cosmological constant, because if he didn't need it, then he didn't see a reason to include it. And it's been coming back and forth in and out of fashion over many decades, depending on what the observations were. Most of the time people didn't include it, but there were other times in the history when, like in the late 1960s, where people saw some certain observations, suddenly it was fashionable again, and then it went away again, and then it came back. And of course in the 1990s, well, there were various reasons for knowing that the universe wasn't described by the model that everybody favoured, which was a certain model with only cold dark matter, in which all the energy density in the universe added up to what's known as critical density, the density which you just need so that things will just keep on expanding forever, because if there's too much matter, then things will want to contract. So there's a thing we call the critical density, and there are various reasons that theorists have based on inflationary cosmology, for which they want something which is very close to critical density. And first of all, in the early 90s, there was a lot of evidence that it wasn't such a critical density universe full of ordinary matter, and then the observation of supernovae really clinched it in the late 1990s, that the expansion of the universe appeared to be accelerating if you use the simple model of Friedman, which has been around since 1922.
That's basically assuming the universe is the same density all the way through. It hasn't got the structures that we know it has, with filaments and voids and
yeah, that's exactly right. So Einstein, of course, included that. Einstein actually wrote down that sort of model in 1917. And it's just that he didn't take the idea of a changing universe seriously, and then Friedman used the same equations, but just took the idea of expansion and contraction seriously. So yes, it does assume that the universe expands just as if everything could be put through a blender to make a uniform soup. I mean, people do know that the universe is inhomogeneous, but what they've always been assuming is that even though it's inhomogeneous, the average expansion is exactly as if there were no structure, and people then always look at it mathematically as if we assume there's no structure and we just add the structures on as perturbations, and if the perturbation theory breaks down, then we do simulations using Newtonian gravity, because it's very difficult to do it with general relativity.
What are the basic ideas for what dark energy is? I know quantum fluctuations of particles popping into and out of existence is one of the current ones.
Well, that's an idea that generally doesn't work in itself. There is something known as the cosmological constant problem, that if you predict what the vacuum energy should be using some rather naive ideas in quantum field theory, then you get something which is out by 120 orders of magnitude.
Much too much energy for what we see.
Yeah, that's right. The universe just wouldn't be here. But that is done without any understanding of what quantum gravity is, and ultimately there are holes in Einstein's theory, and we expect that it should be unified with quantum theory, and then we might understand this question better. But what people have done is to generally you invent some scalar field. That's typically, it's very easy to add sources of matter, or in this case energy, something which doesn't clump gravitationally, so should distinguish dark matter from dark energy. Dark matter would be something which doesn't emit light and is different from all the particles that we're familiar with, but which still forms lumps gravitationally, whereas dark energy is something which is a different type of stuff. It's something which doesn't want to form lumps because it's sort of inherently repulsive. And you can write down very imaginative theories of physics in which you add these sorts of things, and there's zillions and zillions of ways you can do that, things called quintessence, k-essence. You can try and modify the equations of Einstein. Imagine gravity is totally different. But when people do that, they generally imagine gravity is totally different, but still the universe is very simple, because unfortunately it's easy to solve differential equations if the universe is simple. And that's, I think, one of the problems sociologically in the field is that people can think up all sorts of very crazy unknown physics, but they still want to solve simple differential equations rather than dealing with some of the harder conceptual and foundational issues that are in the holes in general relativity, which Einstein left, because you shouldn't think of general relativity as a finished, complete theory. There are really basic questions which Einstein didn't answer. So those are things I've been trying to think about, questions such as what is the biggest particle, what is the biggest object that can move following a path determined by Einstein's equations. I mean, there has to be an answer to that, but those sorts of things weren't put in, and also by Einstein, he didn't answer on what scale do the Einstein equations hold if I cut matter up into arbitrarily large boxes. So in Einstein's equations say that geometry is proportional to matter, so the matter tells space how to curve, but it assumes that you can describe the matter by a fluid, but at some level the fluid description has to break down, especially once structures form and the universe becomes complex. Then things like voids and filaments of galaxies, those certainly are not like particles. They don't have a particle description, so the way in which we describe that matter can be fundamentally different. It's just that it's a too hard problem, we just say, well, let's forget about that. Let's just assume that it is behaving like pressureless dust, and then we add all these extra things because we don't want to go and think about the too hard problem. So a few of us are trying to think about the too hard problem.
You've been doing this research for at least 10 years that I know of, and probably a lot longer. Tell me a little bit about your own views on this matter.
Okay, so I've been working on many other long history in gravitational physics, working on everything from, I started off in my PhD in Cambridge looking at higher dimensions and string theory and things like that, and I've looked at all these other sorts of funny theories that people think about, modified gravity theories with dark energy and all that sort of stuff. In fact, I did a lot of that before the supernova observations came out in the 90s, because there was already enough evidence that the older models didn't work. But it is obvious to everybody who looks at data that, well, the universe is inhomogeneous on some small scales. At late epochs, it started out very smooth. At the time of the Big Bang, it's a reasonable approximation then, well, roughly, to think that the universe is filled with smooth matter fluid, but clearly the universe is very inhomogeneous today. So a number of cosmologists started thinking about those questions in the early 2000s, in particular Thomas Buchert, who's a German cosmologist now working in France for the last 10 years in Lyon, and he put forward a way of taking averages of Einstein's equations which deal with inhomogeneity, but look for something which is close to a smooth average. But what's important in doing that is that you don't necessarily get the equations of Alexander Friedmann back. So in general, you're going to get some different equations. If you assume Einstein's equations hold on small scales, the scales that we actually test it, and then you write down a formalism which takes averages of this, then you end up with different equations. They're the Buchert equations now. So a lot of people were thinking about this, and as soon as you challenge the status quo, there is a lot of debate, and various people weren't happy about this and said, well, there are various problems with this, including, how do you relate these statistical quantities, because that's what he's dealing with, statistical things. How do you relate those statistical quantities to observables, and what is the time slicing here? There are a number of these questions which Buchert's formalism doesn't address directly. So that's where I got interested in the problem, because it's clear that there are many things you can do with the Buchert formalism, but you really need to address some foundational questions to try and answer things such as how do I relate observations to these statistical things. And in all the work that I've done, I've always thought a lot about foundational questions, and so that's when I came in, and I guess the most fun I've had is going back and thinking about redoing thought experiments in the way that Einstein did it back when he was inventing general relativity, to think, well, if he'd had all these observations today, how would he have approached this thought experiment? So in particular, thinking about what is the difference between motion in a completely empty space, a flat space. So how do I distinguish moving in an empty space from being at rest in an expanding space? And at some level, those two notions should be indistinguishable. So what I went in doing that, I extended a principle of Einstein's, the strong equivalence principle, to try and answer that question, because I think with anything, with a universe which is completely inhomogeneous, there has to be simplifying principles to say why the universe appears to be almost homogeneous, even though it's not. And people have conventionally assumed, well, it's just the Friedmann equation, but actually, perhaps it's not the Friedmann equation, but there is a deeper principle in trying to disentangle all of the ideas about distances and redshift. So I added those ingredients to the Buchert equations and ended up with something in which you can sit down and make predictions, and it worked. But it's a very hard job then redoing the whole of cosmology from first principles. So
that's an understatement if ever I've heard one.
What we've done is to look at current supernova data using a very large catalogue of everything that's available, and this is following, there was a big debate when some people pointed out, that were arguing about how statistically significant the signature of acceleration is. But they were just comparing universes which all satisfy the Friedmann equation. So you can have a universe with a dark energy, or you can have a universe which is completely empty and unrealistic, of course, because we know there's matter in the universe, but a universe which is completely empty neither accelerates nor decelerates in its expansion. It would just, you can imagine a universe like this which expands at a constant rate. And then there was argument about how statistically significant it is, because even after 20 years of data, the statistical significance is marginal, not marginal, depending on how you treat things. So we decided to go back and look at the data, because last time that we'd tested things in detail, at that time we got different answers depending on which way we reduced the supernova data. Well, that's to say either my cosmological model, the timescape model, fitted better, or if you use a different method, then the other model fitted better. And it's clear that there are a lot of things that we don't know in the methods about reducing supernova data, because supernovae are not perfect standard candles. There's a lot of uncertainty. So we used the methods of the people who've been questioning the statistical significance of the data, and we also used the methods of their opponents in the debate. And so we found that the new way of doing things, that we get agreement between both ways of reducing the data, and also the timescape model fits with a very, very tiny, it fits better, but only by a very, very tiny amount, so it's nothing to write home about. It's not statistically significant yet, but what is more important from our point of view is that we can see the effect of how the cosmological model that you assume is related to various systematic issues when you reduce the data. So, for example, there's something called the color parameter, and we've done tests that people would ordinarily never do, such as, from the point of view of my cosmological model, the timescape, you shouldn't have an average expansion law if you're using data on small scales below about 450 million light years. So what we did was just not to assume a scale, but to progressively cut data out and see if there's a change in quantities which are supposed to be constant. And lo and behold, there is a change, and the change is roughly at the scale where you expect it. And that's independent of the cosmological model. If you're using my model or their model or an empty universe model, you get the same result. And that means that those sorts of things are going to be important for anyone doing supernova data and trying to understand which is the best model of the universe. So at present, because the uncertainties in the way that we use supernova standard candles, because the uncertainties are so large, we can't say at present which model fits better. But in the 2020s, the Euclid satellite mission, combined with other things about supernova, we should be able to distinguish the models. In fact, we should be able to test the Friedmann equation. So whether my model is the correct way of doing inhomogeneity or some other model is the correct way of doing inhomogeneity, anything which doesn't agree with the Friedmann equation will give a different result by a particular test. So you can test the Friedmann equation itself. And so I have a prediction about the precision of data observational tests that is required in order to see the difference. And other people, there's another back reaction model around called the TARDIS cosmology. They have a prediction also. But in order to actually reach that precision, we've got to understand the supernovae better. And so what we have demonstrated in this latest work is that even if people who are trying to understand dark energy don't accept our model, the very fact that it's not the Friedmann equation that we're using can help them to understand the systematic uncertainties, the unknown astrophysics and the selection biases, because if you only test your data with one model, you can add things and subtract things and do all sorts of things and not realize that actually it's a degeneracy between your cosmological model and some empirical parameter which describes some supernova physics that you don't understand. And so what I'm hoping is that people will start just testing their data and the way that they reduce the data using this cosmological model or some other cosmological model which is not Friedmann, and then maybe we've got some better hope of actually determining what dark energy is.
That's Professor David Wiltshire from the University of Canterbury in New Zealand. And this is SpaceTime. Still to come, the Capstone moon probe finally phones home after mysteriously going silent, and NASA's second launch of the Arnhem Space Centre blasts off to study Alpha Centauri. All that and more still to come on SpaceTime. There are a lot of relieved scientists tonight with NASA's Capstone mission re-establishing contact with mission managers 2 days after mysteriously going silent following its separation from its Rocket Lab Photon Spacecraft. The communications loss raised serious concerns about the mission and whether or not a catastrophic failure had somehow occurred. The 25-kilogram Capstone CubeSat was launched last week aboard an Electron booster from Rocket Lab's Mahia Peninsula Launch Complex on New Zealand's North Island east coast. The Cislunar Autonomous Positioning System Technology Operations and Navigation Experiment, Capstone for short, is designed to test what's known as a near-rectilinear halo orbit, basically a Lagrangian L1 gravitational well between the Earth and the Moon. A place where a spacecraft could maintain a stable orbit between the two celestial bodies, as the gravitational pull from each of the two bodies cancelled each other out. This unique orbital position will eventually become home to the new Lunar Gateway space station, which will be used as a base camp and jumping off point for Artemis missions down to the lunar surface. Capstone was launched into an initial low Earth parking orbit by an Electron rocket, then sent onto a lunar transfer orbit by Photon, gradually increasing its velocity and stretching its orbit into an extreme ellipse around the Earth. Photon then ignited its engine for one final burn, accelerating Capstone with the aid of the Sun's gravity to some 39,500 kilometers an hour on a ballistic lunar transfer trajectory before releasing the probe. The burn is sending Capstone on a 4-month, 1.55 million kilometre journey away from the Earth, more than 3 times the distance between the Earth and the Moon, before gravity finally pulls the little spacecraft back into the Earth-Moon system and settles it into the near rectilinear halo orbit. Now, once in position, Capstone will remain there for the next 6 months, tasked with verifying the region's stability and orbital dynamics. After separating from Photon, Capstone deployed its solar arrays as planned and began preparing its on-orbit propulsion system for the first of its engine burns. It successfully contacted NASA's Deep Space Network during one pass, but achieved only a partial contact on the second, and then nothing. The spacecraft mysteriously went silent, and mission managers still don't know why. But the spacecraft has now re-established communications and is looking happy and healthy. The loss of contact meant scrubbing the spacecraft's first trajectory correction engine burn, but that's an issue which can be rectified on the next burn. We'll keep you informed. This is SpaceTime. Still to come, NASA's second launch from the Arnhem Space Centre blasts off to study Alpha Centauri, and later in the science report, doctors warn of a new, more infectious third COVID Omicron wave on its way. All that and more still to come on SpaceTime. NASA has conducted a second launch from the Arnhem Space Centre, sending a suborbital sounding rocket on a mission to study our nearest neighbouring star system, Alpha Centauri. The flight, named SpaceTime, was designed to study ultraviolet light from the 2 primary stars in the triple-star Alpha Centauri system. The launch had been delayed several days by high winds. SpaceTime is meant to stand for Suborbital Imaging Spectrograph for Transition Region Radiance from nearby exoplanet host stars. It was developed by the University of Colorado Boulder. It's designed to study how the ultraviolet light from the 2 stars, Alpha Centauri A, which is a spectral type G yellow dwarf star, similar but a little bit bigger than our Sun, and Alpha Centauri B, a less massive spectral type K orange dwarf star, a little smaller than our Sun, is likely to impact the atmosphere of any planet orbiting around the pair.
All the things we sort of take for granted that happen here on Earth with our sun, we just don't know those things about planets around other stars, and so that's what we're here to measure.
Alpha Centauri A and B orbit each other in a binary system, and are in turn orbited by the third star in the system, a spectral type M red dwarf star known as Proxima Centauri, which at 4.25 light-years distant is the nearest star to the Earth other than the Sun. The mission aboard a 13-metre-long Black Brant 9 sounding rocket follows on from last week's successful launch, which studied Alpha Centauri using an X-ray quantum calorimeter developed by the University of Wisconsin in Madison. That flight used unique X-ray detectors, cooled down to just 1/20th of a degree above absolute zero, to measure X-rays in the interstellar medium, that's the space between the stars, with unprecedented precision. The third mission, which is slated to launch this week, will carry JUICE, the dual-channel extreme ultraviolet continuum experiment, also developed by the University of Colorado Boulder. JUICE will measure a so far unstudied part of the ultraviolet spectrum from stars less massive than the Sun and check out its effect on the atmospheres of any orbiting planets. The Arnhem Space Centre was selected as preferred launch site for these missions because of its location, allowing astrophysics studies that can only be done from the southern hemisphere. Located just 12 degrees south of the equator on the Gulf of Carpentaria, the Arnhem Space Centre near Nhulunbuy, 640 kilometres east of Darwin in the Northern Territory outback, is ideally suited for equatorial missions. The complex is developing 3 launch pads, allowing it to undertake up to 50 flights a year. Meanwhile, work continues on 3 other commercial launch facilities across Australia. Southern Launch are developing a polar launch facility at a place called Whalers Way. That's on South Australia's Eyre Peninsula near Port Lincoln. It would undertake flights over the Great Southern Ocean on polar orbits, often used by scientific and intelligence-gathering spacecraft. Southern Launch also operates a rocket test range at Kiniba, 40 kilometres from Ceduna on the South Australian west coast. It tracks west over the Nullarbor Plain, allowing the testing and retrieval of rockets and their payloads. Meanwhile, construction is also proceeding in North Queensland on the Bowen Spaceport at Abbott Point, which will be used for equatorial launches by Gilmour Space Technologies' new Ares rocket, which will fly east over the South Pacific Ocean. That's expected to launch its first mission later this year. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. The Australian government has decided to proceed with a fourth COVID-19 vaccination dose for people aged 30 and older. The fourth shot's already available for senior citizens aged over 65. The move comes in the wake of the spread of the more infectious BA4 and BA5 subvariants of Omicron, which first appeared in South Africa in January and February this year. These new mutations have learnt how to evade immune responses, and they even ignore vaccine-induced antibodies. This allows the new variants not just to infect more people, but also reinfect people who were previously infected and have recovered. The original China Wuhan strain of COVID-19 had an RO rating of 3.3, meaning every infected person was likely to infect an average of at least 3.3 more people. The Delta strain, which was the big boogeyman last year, increased that infection rate to 5.1, while the original Omicron BA1 strain saw that number jump all the way to 9.5. The BA2 strain, which is currently the dominant variant in Australia, has seen another big jump in infection rates to 13.3. Preprint, non-peer-reviewed studies in South Africa looking at the new BA4 and BA5 subvariants suggest an RO rating of around 18.6, a massive jump, meaning that every infected person is likely to infect at least another 18 to 19 people. Now, to put that in context, that's a similar rate to measles, which until now was the most infectious viral disease for humans. Over 6.4 million people have now been killed by the COVID-19 coronavirus since it first appeared in the area around China's Wuhan Institute of Virology back in September 2019. However, the World Health Organization says the true death toll is likely to be around 15 million, with over 560 million confirmed cases globally. A new study claims people who eat a diet rich in vitamin K can have a 34% lower risk of arteriosclerosis-related cardiovascular disease. The findings, reported in the Journal of the American Heart Association, are based on data from more than 50,000 people taking part in the Danish Diet, Cancer and Health study over a 23-year period. Scientists at Edith Cowan University investigated whether people who ate more foods containing vitamin K had a lower risk of cardiovascular disease related to arteriosclerosis, which is a plaque buildup in the arteries. There are two types of vitamin K found in foods we eat. Vitamin K1 comes primarily from green leafy vegetables and vegetable oils, while vitamin K2 is found in meat, eggs, and fermented foods such as cheese. The study found that people with the highest intakes of vitamin K1 were 21% less likely to be hospitalized with cardiovascular disease related to arteriosclerosis. And for vitamin K2, the risk of being hospitalized was 14% lower. A new study has found that true believers, whose identity is strongly fused with their cause, are usually the most willing to fight and die for that cause. The findings, reported in the journal Frontiers in Psychology, looked at two causes, Second Amendment gun rights and abortion rights, and found that if one considers a value to be sacred, considers it to be a moral conviction, or if identity is fused with a cause, one might be more likely and more willing to fight and die for that cause. The authors say the findings suggest that people who are strongly fused with their cause and experience what they believe to be a threat to it are likely to become radicalized. They also suggest that shifting radicals from fusion with an extreme cause to a benevolent cause may well transform them from a force of evil to a force of good. A new book looks at the high levels of junk science, which often finds its way into forensic sciences. From lie-detecting polygraphs to bite marks, this book carefully and unarguably explains that many things which have in the past been paraded in courts of law as scientific fact are often unreliable and commonly entirely bogus. Tim Minham from Australian Skeptics says the problem isn't just polygraphs, but arson investigations, hair microscopy, bullet lead analyses, voice spectrometry, handwriting, and even blood-stain spatter analysis.
Yeah, this is the thing. I mean, and I like the way you say forensic science, because thank heavens you did, because the actual definition of forensic is to do with the law, to do with courts. So you have forensic science, you have forensic medicine, you have forensic accounting, all sorts of things. So the forensic just means it's used in courts, etc. But forensic science has obviously a cachet because it's now popular. It's been popular in TV shows and things where the fellow who goes out to the crime scene, the scientific person, and collects information, etc., and then comes back with their expert opinion. Happens a lot in psychology as well. Obviously, we've seen that. The problem is you're seeing things that are used in forensic science that they think are accurate objective measures, where they're actually very subjective measures. The classic example is the polygraph or the lie detector.
Yeah, I thought polygraphs were real. I thought they were something that proved if you were lying or not, but we now know they're not. And it's the same with body language. I always thought that was real because that's what they said on telly, but we now know there's very little relationship with what a person's really thinking.
Yeah, I mean, this particular story now came out of an article of someone who was looking at a book about sort of forensics and saying that most of the forensic science you see used in court, especially obviously in the media, but actually used in court, is dodgy, to say the best. Now, the polygraph, the lie detector, if you had been reading the skeptical literature, you would know for decades that it's poor, very, very poor. A lie detector does not measure lies, it measures stress. This can be very different things, and people undergoing a lie detector test tend to be under stress for a start. And there's been examples used where people sort of, a question is asked of a person who's wired up, and that is when you did this, knowing full well they didn't. And even though they might say, no, I didn't do that, the little graph will go up, shooting up, etc., indicating a lie. Well, it's not. It indicates stress. And it's totally different things. And so that use of polygraph, in fact, I think these days in courts is not allowed because they know it just doesn't work. It applies to a lot of other areas. This particular thing says bite marks, blood splatters, voice spectrometry, handwriting analysis, all sorts of hair microscopy, all sorts of things that are used, some of them routinely in forensic science, have very little justification. You obviously end up with, forget the media, forget the CSI programs and that sort of thing for the start. Let's look at the actual use of it. You do get people who get carried away by the fame of being a forensic science expert and expert opinion that's being used in courts, etc. Some of them are. Some of them are experts,
etc. They make a living out of it, don't they? That's
right. And they get a lot of credibility out of it, and it might be good for their profession, etc. All sorts of things like that. They become a noted expert on a particular topic.
I keep thinking of the famous Lindy Chamberlain case with Azaria and the blood spatter in the Holden Tirana, which turned out not to be blood spatter at all, but insulation glue.
Yeah, I know. I mean, and this is the problem, that especially in high-profile cases, people get carried away with the evidence, of the evidence in quotes that's being put forward from a forensic science point of view. Now, there is real forensic science, and it's really used in cases. The question is, how reliable is it and how much credibility you should give to it? And this particular book says about the only thing that is credible is DNA analysis, which is pretty objective. You analyze the DNA, you see it, the DNA thread, you compare it with other DNA. If it matches, there's a pretty good chance that is an indication
Assuming there's no contamination, of course.
That's the other area. Yeah, I mean, and that's the case of all these things. But some of these, when you're testing teeth marks or bite marks, it's very subjective as to what matches or not. But, DNA comes closer to being truly scientific and testable and repeatable, whereas a lot of these other things are not. And so it's a simple matter of realising that despite what you see in the movies and TV, people running around doing lie detector tests, practitioners wearing lab coats, don't know why. They wear lab coats, makes them look more sciencey. And that sort of stuff is take everything like that with skepticism and also a grain of salt. So that's the thing to watch out for. That's what this book talks about. Obviously, some people might have a bit of vested interest because the guy who wrote the book does DNA analysis, so that might be an issue there as well. But it's very interesting. Skeptics have been talking about this for yonks. Other people are only just discovering it. They're mainly because it's done with such conviction in TV shows and that sort of thing.
That's Tim Mendham from Australian Skeptics. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more space time, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.